Hello and welcome. Today we're doing a Q&A 4 o'clock session on... So I didn't get through all the questions from Saturday's live stream, so I'm going to start with those. I checked my email a few moments ago to see if there's any new messages, but I didn't see anything. I'll do a quick last check. If there's any emails that have since come through in the past 20 minutes. Oh, got one. Got two. Okay. I will add these to the list, so just give me one moment. It's alright. Okay. Hopefully this is working now. If I refresh my browser, do I show up on my own YouTube studio? It's doing something. This isn't a... Oh, I am online?
You're just offline.
Just offline.
Yeah.
Okay, so it looks like... Okay. So it looks like it was just a really long lag. Okay. Can you let people know in the feed? So probably the lag was longer than a minute or two, so therefore you didn't see it. Therefore, I now have a duplicate live stream now.
Okay.
So if people are still in the old chat, ask them to refresh on the main page to go to the new live stream if the video's cut.
Okay.
Thank you.
Did you get to that zero factorial question?
Yeah.
Oh.
I did. I posted it as a comment. Yeah. Sorry about that, folks. I had to restart the live stream. Apparently the lag or delay sort of indicated that it wasn't happening, but apparently it did. So. Alright, so the first the first few questions from yesterday, Amy and Josh essentially asked the same question, which was how to work out the last question of the practice exam for maths. So I've just sort of taken some of the details from the question, and then I'm just going to give it a go, trying to solve it. Hopefully my handwriting is still large enough for you to see on the stream itself. I do want to take some shortcuts with this solution because there's still quite a lot of leftover questions from yesterday, so I am going to take a shortcut by actually using a calculator to do some of the decimal multiplication. So you've seen how to do it before. I showed you how to do decimal calculations with multiplication and division yesterday in yesterday's live stream. I think it was one of Lauren's questions. So I'm just going to have that as assumed knowledge, as a shortcut, just so we can get through more questions. Otherwise, we'll be here all day watching me struggle. Okay, so this one here was about a car fuel efficiency. The question says, a car uses 25% less fuel per kilometer when traveling at 90 kilometers per hour than it would when it's traveling at 110 kilometers per hour. Janelle's car uses 7.8 liters of fuel per 100 kilometers when traveling at 110 kilometers per hour, and fuel costs 155.9 cents per liter. Determine how much money Janelle would save on a 1,000 kilometer trip if she travels at 90 kilometers per hour instead of 110 kilometers per hour, and round to the nearest cent. Alright, that is quite a lot of info in the question itself, so my go-to approach would be highlighting. So I'd get a nice bright color, I would highlight all the numbers, I would try and highlight the number and the information that goes with it. So for example, 25% less fuel at 90 kilometers per hour than 110 kilometers per hour. So just trying to highlight the numbers and some of the words that go with it to give it context. Another approach that you can see already done, I've actually sort of tried to extract from the question and stick a little bit of a list of information. And sometimes I find when I extract information from the word problem, it's just easier to try and digest this than it is to try and digest the sort of paragraph that's in the exam paper. So I basically need to figure out how much fuel she spends on a 1,000-kilometer trip. And I know from the question it says she uses 7.8 liters per 100 kilometers per hour, per 100 kilometers. So that's just going to be multiplying the 7.8 liters. I'm just going to multiply that by 10, aren't I? So fuel, oh goodness me, why am I spelling badly on live? Fuel at her regular speed for 1,000 kilometers. Okay, so I need to calculate this. This is, you can imagine this as like the K for Kiwa, Kiwa structure. So that's going to be 7.8 liters per. When you see the word per, that often means like you've got a fraction happening there. So this is on top, this is on bottom. So that's where this information is coming from. Okay, and I know that this trip is 1,000 kilometers, so all I have to do is just scale this fraction 10 times, top and bottom, and that would give me 1,000 kilometers on the bottom, and obviously 7.8 liters on the top. So therefore, she uses 78 liters for 1,000 kilometer trip. Okay, so now I know how much fuel she uses at 110 kilometers per hour. Now I'm just going to figure out how much is that going to cost her. So let's do the cost. So I'm going to take this number here and move it into my next bit of working. Notice how I'm using arrows. Okay, so if you have a lot of calculations that go across the page, it is super helpful for us as teachers, or even just people who are marking your exams. Let's say you're doing an external exam, meaning you do it and then it just gets taken away by the country, and then somebody in another state will mark it for you. It's really helpful if you have any little signs that can lead the reader through what you're trying to do. So I'm using arrows, I use English, little English words here and there. Okay, so let's do the cost of that. So cost at the 110 kilometers per hour, because that's what my first calculation is all about. That's going to be equal to the liters, 78 liters, multiplied by the cost of fuel. The cost of fuel is here, 155.9 cents per liter. I think it's going to make the most sense to represent my final answer in terms of dollars rather than in terms of cents. So I'm just going to quickly convert the 155.9. I'm just going to convert that into dollars. That'll be $1.559. Okay, so that's going to be $1.559. Just do the maths. Now here's where the shortcut's happening. I'm going to use my little calculator here. 78 liters times by 1.559. I get an answer of 121.6, and I have to round to the nearest cent, so I might leave the cents here for now, and it might carry across to the very end of my answer. So I won't throw it away yet. Rounding your answer is only a good idea at the very, very, very end. If you round too early and you're constantly rounding your answers as you go through your procedure, it'll accumulate problems. Okay, so that's her cost. Okay, the other part of the question is like, well, how much would she save if she drives at the slower speed, which apparently is more fuel efficient? So let's go. How much fuel efficient? Well, it's going to be 25% less fuel. Okay, so let's work on that. I'll even color coordinate that. So I'm going to take the amount of fuel, which we already calculated was 78 liters. Let's do 25% less of that. So I'm going to do 78 liters minus 25% of 78 liters. Okay, so this will be, why am I spelling it wrong? Fuel at 90 kilometers per hour. Okay, so that's my little K for Kiwa is equal to 78 liters, remove 25% of, so that's going to be 78 minus 25 out of 100 times by 78 over 1, and I'm going to take a bit of a shortcut again. Another approach that I could have done is 78 liters times by 75%, because think about it, if I've removed 25%, how much is left remaining? So that's another way of looking at it. I could also say that this line and this line they are equivalent responses here. So I could just do times by 75 over 100, okay, or basically 0.75. So I'm going to smash this on the calculator here. 78 litres times by 0.75. I get an answer of 58.5 litres. Okay, so there's how much fuel she uses at the slower speed. Now let's figure out how much that's going to cost us. So let's go to cost. So here, cost at 90 kilometers per hour. Okay, this is going to be equal to the litres she uses multiplied by the cost per litre. So again, I'm going to use the answer in dollars, so $1.559. Use my calculator again here to save us all some time. 58.5 multiplied by 1.559. I get a result of $91.2015. Am I finished? No. Usually when I get to about here, I think that I'm done. I will actually check the question once more time. So that's what I'm doing right now. I've gotten as far as I think I need to go, and now I'm just going to double check it. Determine how much money Janelle would save on a 1,000 kilometer trip if she travels at 90 versus 110 kilometers per hour and round. So it's about how much money she would save, not how much money she would pay. So saving would imply that there's a difference between the costs. So let's do a difference. I'm going to calculate that in, I'm going to use purple. Okay, so I'm going to lead from here to here. So savings would be equal to the full price.
Hold on, you have a really bad line in history.
Well, I don't know what to do about that. I'm just going to carry forward.
Okay.
There's nothing I can do.
Yeah, a lot of people are trying to get it on it as well. So I don't know if it's happening.
Getting lots
Now it's
offline. I'm getting inconsistent. Let's see. If I turn that Wi-Fi off. How about now? Is that better? Yeah. Okay. Sorry, folks. My wife informed me there was a lot of terrible lag. I just had to turn off the Wi-Fi off of my phone, which I'm streaming from, so that's probably why. It was probably just sitting on the Wi-Fi instead of... hopefully you can still read what I'm solving here. I'm going to calculate the difference here in the two costs, remove the lower cost, 91.215, and again I'm going to use the calculator to save myself time, 121.602, remove 91.2015, get a savings of $30.40. And the question says round to the nearest cent, so I'm just going to round off my trailing decimals here. And that's my answer. If I check the answer scheme of the exam, yeah, my answer matches, so that's a positive sign. Okay, so question 11, quite a big task. The strategies that I applied was highlighting, if I have that option. Obviously it's on my computer screen, so I couldn't physically highlight my screen. Second strategy that I used is that I tried to extract the numbers and put them in a little bit of like a short list. Then I used that short list to try and decide where do I begin. I need to figure out how much fuel she's using. I used this trick here where I saw the word, sorry, let me just erase this bit here. Let me just look at this. I saw this line here. In the English, the way it's written on the exam paper, and I know that when you see the word per, that means divide or also means a fraction. So I used that to turn into that, and then from there I could see, oh, okay, well if I just want to find out how much fuel she uses for a 1,000 kilometer trip, then I just need to scale it up. So that was basically my launching point, and once I got that, I could easily find out how much fuel she used in total. And then I use that total cost to calculate, total fuel to find the cost, and from there I could do a percentage removal for savings and stuff like that. So I hope that helps. We had another question, moving on from Amy and Josh's question, because question 29 and 30 are basically the same question. I'm just talking to my wife just now. Ruby asks, can you go over quantities and proportions? So the idea about proportions is that you can represent them as a percentage, a fraction, or a ratio. So let's say, for instance, your body is made of 50% water. I know that's not accurate. I know it's more to it than that. It's more complicated. But let's just pretend, for just simplicity's sake here, I could show the proportion of water by representing the quantity in the percentage. I could also represent that proportion in terms of fraction form. So like 1 out of 2, or 1 part out of 2 of your body is made of water. That's the same thing as saying the body is 50% water. The other way I can go about this is I can represent a proportion as a ratio. Okay, 50 is to 50, or 1 to 1 basically.
So did you just cover question
10? No, I haven't done 10 yet.
10? Okay, great.
That'll be after.
There's a lot of people asking about that.
Oh, a lot about, and that's the money one? Okay. I do have question 10 lower on my little notes here, everyone, so I will get to that, just that Ruby got it a bit earlier. For ratio, I could show it's 50-50. Technically, I would simplify that to 1-to-1 ratio there, where for every 1 part water, you have 1 part of something else in your body. Could be bones, muscles, all that thing that's put together. So what we're doing with this concept is basically they're trying to stretch your skills to convert some of the English into one of these forms, okay? So you have to convert into this form, or this form, or this form, okay? First one here is like represent 6 out of 20 as a fraction. So this is already showing a proportion, how much out of something else. So that's pretty basic. The fraction is just going to be 6 out of. Out of means divided, or it also means the fraction sign. I would personally go further and simplify that. So I could divide top and bottom by 3. So I would get 2 out of 10. Oh, hang on, is that this? 6 divided by 3 is 2. No, I can't divide top and bottom by 3. I have to divide top and bottom by I would get this answer. No. This answer. Sorry, buddy. I'm not on my top form today. 3 out of 10. So that'll be the simplest form for that fraction. Moving on. Here's another type of question you might be presented with, where they're going to describe to you quantities of things that are related in terms of proportions, like how much of this versus another object. So here I've got basic pancake recipe. You'll find that this generally works. Pancakes are 3 parts milk. So I could represent this as a ratio if I wanted to, just down the side. So 3 parts is to 1 part egg, so 1 part eggs, is to 2 parts flour. So that's another way of showing that information on in a proportion. But the question I actually wrote here is represent the proportion of flour as a percentage of the total. So we want to go with this format, okay, the green one. So I need to find out how much flour that is. Often when you want to do percentages with proportions, or with with proportions or ratios, you basically have to start with fraction. Fraction is a really good starting point for almost everything. It's probably the reason why we did so much work last term on fractions alone. So I'm going to turn this into a fraction, and then I can convert that into a percentage here. So the amount of flour, okay, so we have 2 parts flour, so 2 parts flour, for example, out of the total. So what is the total? Well, I have to count up all the parts, don't I? 3 parts plus 1 part, that makes 4 so far, plus another 2 parts, that gives us 6 parts in total. So I got 6 parts total. And the thing about fractions, or ratios for that matter, is that not only can you divide top and bottom by a common factor, you can also divide things by common units. So parts divided by parts actually cancels out to make 1, 1. 2 divided by 2 gives me 1. 6 divided by 2 gives me 3. So the ratio is actually 1/3. That is a fraction of the total, but I need to do that in percentage. So the conversion process is, so I'm going to now change my color here to do percentage. Let me just set this aside and shrink that down. So the percentage would be the 1/3. So I needed that part, so I'm carrying that across. And to convert anything into a percentage, you're basically going to multiply it by 100%, which is also basically 100 over 1. So I'm just going to have 100 over 3%, which I think we'll get to, I get 33.3 recurring percent. All right, so hope that helps, Ruby. Moving on to Brooke. Brooke asks about question 5A, B, and C. I think I will do... Oh, that's right. Amy already asked about question 10 as well. So this, I'm going to, before I get to question 5 of the practice test, I'm going to do question 10, which I think everyone's very keen to hear about. The baby mouse doubles in weight every week from birth. For example, after 3 weeks, the baby mouse is 8 times its original birth weight. And the question asks us, question 10, determine how much bigger the baby mouse is after 5 weeks compared to its birth weight. So, one way of doing it, the way I thought about doing it is just doing it like bit by bit. So, after 1 week, so this is like, you can imagine weeks, okay? And this is times, okay? So after 1 week, the baby mouse will be twice or 2 times its original weight. After 2 weeks, it'll be double again. So what's double twice? Well, you get 4. Okay. After 3 weeks, what's double that again? So double 4, well, it gives me 8. And I'm just going to keep the little sequence going. Okay, so I get an answer of the baby mouse will be 32 times bigger. Will be 32 times heavier than birth. Okay, I'm not particularly being careful about my handwriting because I'm very conscious of how long each of these things will take me to solve if I do everything very, very perfectly neat. B asks, write an expression, so that's going to be algebra, letters and numbers. Write an expression using powers for how much bigger the baby mouse is after 5 weeks. So how can I show 32 in power form? Well, I basically, the process that was happening up here, particularly in this sequence here, 2, 4, 8, 16, I'm basically doubling every time. And when you double every time, it's 2 times 2 times 2 times... Okay, so that same thing is going to be twice times 2. Okay, count them all up. That's going to be the same thing as 2 to the power of 5, which I think that matches the original question there. Okay, so moving on to letter C of that question. Determine how many weeks it would take for the baby mouse to be 256 times as big. Show all the working. So what Miss Appleton has done there is she's calculated everything. She did calculations like 2 squared gives you 4, 2 cubed would give you, 8, 2 to the power of 4, and so on. What I was thinking of when I was looking at this question here is I just basically continued my little table here. I went to like 6, 7, 8, alright? So let's do that. So I already know what 5 weeks is worth. 6, 7, 8. Alright, so 5 weeks was 32 times bigger. 6 weeks later will be double again, so that gives me 64. 7 weeks will be double that again, 128. And why do I know these numbers off the top of my head? Well, that's basically how all of computer's storage is done. So 2, 4, 8, 16, 32, 64, 128, 256, 512, 124, 2048. You just recognize those numbers all the time because of like when you buy a hard drive for your computer, when you buy a USB drive and you stick it in, they often have these particular numbers. Anyway, so next number is 256. Okay, so that's the answer. It's going to be 8 weeks. It will be 256 times bigger after 8 weeks. Okay, so there's 2 ways of getting to the answer. If you follow Miss Appleton's style, you can get to the same result. If you follow my little table, that's also another way of doing it. Letter D. Write an expression using powers or index notation that describes how many times bigger the mouse will be after n weeks of life.
Offline.
Offline. I'm still seeing... Ooh, something cut out. Okay, I'm seeing... Ooh, that is a bit inconsistent.
Oh, you're back? Okay.
Yeah, I'm seeing...
Your lag is low.
Yeah, So everybody, apparently we're experiencing some serious lag. I can't do anything about it. Phone internet is faster than home internet, but it's inconsistent, so it'll be up and down. So I'll try and keep an eye on the upload rate, which is low. Okay, so I have to calculate. I have to represent a formula basically that will represent how heavy the baby mouse will be after n weeks of life, and define your own variable for birth weight. Okay, so this probably is what I was trying to do in the last video, where I was basically trying to solve letter D when I was actually supposed to be answering letter B. So we know that the weight of the baby mouse will be scaled by a factor of twice. So I'm going to put 2w. It'll be scaled by twice for every week. Okay, so if the week is 1, then it'll be just 2 to the power of 1. If it's been 2 weeks later, it'll be 2 to the power of 2. If it's 3 weeks later, it'll be 2 to the power of 3. And if they're saying n weeks of life, then I can just say for all values of n. So there's a little formula there. I can't really think of a way to show you the working besides what I just described now. Did I cut out again, or?
No, you're fine.
Okay. What you might do just to polish it off is define what the letter W means. So I'm just going to say where W equals the weight, birth weight, sorry. So the original weight of the mouse. Okay. That's it. So moving on to the next question. So we got Brooke asks, you know what? I might do some quick questions off the list. Ooh, there's quite a lot of questions. So if Jess can knock out some of the questions that I've already solved. So I've already solved these. Okay. Brooke asked, can you explain how lightning works? Not very well. I do know there's about friction in the air. I'm not going to say anything more about that because I don't want to say things that are wrong, so I'm just sort of speculating at this point. I can't really tell you, but that sort of implies that you don't really need to know that if you're doing the test. Lightning is not at the forefront of what's important. So we can remove that question there. That's number 31. Brooke also asks, I might try someone else. Brian says, what is a fulcrum? A fulcrum is a resting place for a lever. It could be a hinge or a resting pivot point. So a fulcrum could be, so if I've got a rock, okay, and I've got, here's my beam that I'm trying to use to sort of lift the rock over. My fulcrum could be another rock over here. That way, when I apply my effort, I could sort of rest upon this at this point here. So a fulcrum is basically a resting point or a hinge. Another variation of this one is that you could have a fulcrum right over here. All right, I think you might recognize this object. If I just continue adding a few things here. So this is basically scissors, right? So I've essentially got a lever this way, and I've also got a lever this way. So 2 levers, and they're both sharing the same fulcrum or pivot point. So I hope that answers Brian's question. Oh, you already taken it out? Quick, cool. Brooke asks, how are magnetic field lines similar to the lines on a basketball court? Okay, so that's one of my questions from the little practice test. So I think a basketball court looks something like, I think there's like a key in there, isn't there? Something like that, and some little markings around here. So the idea I had with the question was that the basketball court designates the area where the players can play basketball. If you're outside of lines, you're not allowed to play there. Like, you know, it wouldn't be fair if you're like, take the ball. So if you're here, it wouldn't be fair if you went right out the bounds and came around the back and then shot it into the hoop. That's not fair. So the lines of the basketball court designate where you are allowed to play or where you find the basketball players. If we look at a magnet, okay, and here's my north and south ends of that pole, these magnetic field lines are a little bit like the basketball court, where these magnetic field lines represent the area of influence that the magnetic force has. Okay, and the closer these lines are together, the stronger the magnetic force will become. So I guess you could draw a parallel where the actual hoops, you know, there's the backboard and here's my basketball net. You'll find that the lines tend to be more closer together around the two ends, very similar how you find the lines very close together, the two ends of a magnet. So there's a couple of comparisons there. The idea being it's where you're allowed to play, or it's where the magnetic force can play. Any other quick questions? I'll look at the chat feed questions before I go back to the ones from yesterday. What a balance force is. Balance force, this is for question 1 of the chat feed, so Cochrane, thank you. Balance force is basically when the forces cancel out. So if I am sitting on a chair, okay, I'm going to have my weight, and the chair is going to resist me by the same strength. Okay, so this will be the normal force. Okay, if these two forces are equal, they cancel out. They cancel out each other's acceleration, meaning that when I'm sitting on there, I don't particularly accelerate upwards, I don't particularly accelerate downwards, because overall, that sort of tug of war, no one wins. Everyone is even. Everyone is technically balanced. So that's the idea about balance forces. Okay, so whenever you find the arrows all basically cancel each other out, that will be a balanced, those forces are balanced. So that's question 1. Charudi asks, what is normal force? Normal force is the repulsion between that occurs between two objects when they touch. So Charudi, you're not one of my students for science, but I imagine if your teacher might have called it, your teachers may have presented this information in terms of Newton's third law of motion, if that rings a bell for you. So there's 3 laws of motion. Let's just do that on the okay. Okay. He has, number 1 is the concept of inertia or momentum. Okay. The second concept is force makes things accelerate. And you might recognize this little rule here. And the last one is for every action there is an equal and opposite reaction. Meaning that, and this is the one that's going to be related to the normal force there. So if there's an action force, there's going to be a repelling force. There's going to be something working the other way. So for example, if let's say I've got a student of mine who tends to rock his chair a little too often in science class. Okay, you know who you are. And let's say another student is throwing things in the room. You also know who you are. Okay, so here they have thrown an object at my poor student who's doing the wrong thing. Okay, when that ball makes contact with my student's head, it's going to apply a force, isn't it? So it's going to push that way. But so this moment of contact, there's going to be pushing going on. If the ball hasn't made contact, so if I just grab this, oops, oh, took his head off. Okay, if the ball hasn't made contact yet, okay, the only force that's acting on this object here is just the weight, okay? But when the ball finally reaches my student's head, I'm just enjoying this for a moment here, just hypothetically. So when that thing makes contact with the student's head, that will momentarily apply a force to his head. So there will be a push, wasn't there? However, you notice that when this occurs, the ball doesn't just go and then just drop to the ground. The ball goes and repels away. What's done that? Well, that's the kid's head repelling the ball away. So there will be a reaction force. Okay, so you can imagine the push of the ball on the head, that's the action, or action force, applied force, and then the reaction will be the ball being repelled backwards as well. Okay, I've been calling these sorts of situations where we're talking about the normal force, where basically, and I think someone else mentioned, this overlaps with, somebody else asked the previous day, yeah, question 36 from yesterday, Alex asked, can you go over the normal force? Normal force actually comes from the repulsion between atoms, okay? So if you remember that inside of an atom, I'm going to use my highlighter here. So inside of an atom, you've got some protons, which are positive, and you'll also have some neutrons, which are neutral, and you'll have some electrons, okay, around the outside of your atom, okay? I think you recognize these things. The problem is that these are all negatively charged, okay? So if your butt, so I've been calling it the butt, so let me just, is it too graphic to draw a hypothetical butt on a live stream?
What?
Okay, so I'm just going to draw it. Okay, so here's the butt, and then we got a chair, okay? There's the chair. Your butt's got atoms as well, right? So I'm going to have, let me just draw a very simple small atom here for a moment. I'm going to draw 1, 2, 3, 1, 2, 3, 4, 1, 2, 3. Okay. The chat feed going crazy, is it?
No.
Okay. Okay, so just putting some atoms on your butt. Okay, so not only do the atoms inside your butt repel each other away, they're also going to repel other atoms in the chair. Okay, so when we're looking right here between your butt and the chair, these negative charges are actually going to repel each other away, because we know that's the electrostatic force, where like charges actually repel each other away. So you can see that the closer you are between the two surfaces, so if you slam your butt really hard into a chair, you bring those atoms very close together and they are going to push each other away. So basically, the harder these two things make contact, the repelling force is going to get stronger by the same token, by the same strength, which is why generally when you have something hitting your head like this, your head feels the same force as that ball has when it bounces away from your head. Hope that helps answer Charudi's and Alex's question. Any other quick questions? Going to go over 15% question 9A. How do ball bearings in wheels reduce friction? Ball bearings basically reduce the surface area between the inside of your wheel and the outside of the wheel. So I'm just going to do a really complicated diagram here, so give me a moment. Okay. Okay, I think you can imagine this is a wheel, like a car tire. The thing is that if you want your wheels to spin really nice and freely, okay, then you're going to have a problem right here where the axle meets the interior of the wheel. If it's just a cylinder sitting on a tube, then there's a lot of surface area there to basically rub against one another. And we know that surface area tends to make friction worse. Okay, so for example, ice skates do this sort of thing where they have very little surface area touching the ground. I don't have a lot of time to go into that, but just take my word for it. The more surface area, the more friction you'll experience, more resistance to spinning. So what you could do, instead of having the two surfaces actually meet, what if you put tiny spheres in that, well, come on, tiny spheres in that gap. meaning that the only areas of contact is going to be these 2 points around each one of these ball bearings. That's the concept. You might have some contact between the ball bearings, so that's, you know, maybe 2 up to 4 points of contact, but you would agree that's a lot less surface in contact. Plus the spheres can just roll over rather than just sit there and just grind. Okay, they'll just roll if they need to. So that just makes the whole process, like the wheel, spin longer. So that's why you get fidget spinners that can spin for quite a while. That takes care of that question there. Will torque be a definition of the science test? No. That's number 8 of the chat feed. Please go over the FW equals something and the other formula. Yeah. Okay, there's a couple of people asking about force. Let's do the force formula.
Also, next time we should do the one just above it. We can talk definition of the test question.
Which one?
Just above it.
Torque. I said, yeah, torque definition will not be on the science test. That's number 8. You can remove that one. Okay. Force. You know the definition of force. It's a push, pull, or twist action on an object, and that'll make the object accelerate in that direction or decelerate if the force is acting in opposition to the object's original movement. So if this fist is coming towards you and I have a rubber band attached to my hand around my neck and around the band here, okay, so something like that, then as I try and move, the rubber band will start to pull back on my hand, so it's going to slow my hand down as it tries to move against you. So it can make things accelerate in the direction of the force. It can make objects decelerate or slow down if the force is acting in the opposite direction, or it could change the object's shape. So if you imagine a car crash, all the metal basically changes shape and absorbs that energy. Force can also be described mathematically, okay, using this equation. Okay, force is equal to the mass times acceleration. So the more mass you have, the more difficult it will become to accelerate the object. So for example, if I have a very heavy shopping trolley and I push it with all of my strength, I'll only get it'll accelerate very slowly. But and that's for a given, like, my maximum force. Okay, I can't assuming I'm pushing the trolley as hard as I can in every situation. So I push as hard as I can, but if the object's really heavy, I'll only get a little bit of acceleration. But vice versa, if I push with all my strength and a shopping trolley is practically empty, okay, so I've only got just a little bit of mass, I'm going to get a huge acceleration out of that object. So that's just a mathematical way of showing how much force will make things accelerate how much. We've been calculating things that we know that weight, for example, weight is a force where any object with mass is being pulled to a source of gravity. So you're pulled to the Earth is pulled to you, there's an attraction force bringing you two together. We can actually, and it's a force, so we can actually show that using FW. So I'm using the W subscript. Subscript is anything that's sort of below the, if you imagine like a middle line here, subscript would be any letters you find sort of sunken down below the line. Kind of like you know how you have got powers, for example, they sit above the line. They would be called a superscript. Subscripts are the things that tend to sit on the below the line, okay? So force weight is going to be equal to, let me just clear this out, is equal to mass times a different letter. This letter here is the acceleration due to gravity. Okay? So on the Earth, this actually has a constant value, kind of like pi has that constant value of 3.14 something something something. G on the Earth has a constant value of 9.81. It also has a unit, okay, just like kilometers per hour or seconds or meters or, grams. It has a unit of meters per second squared, okay? That's just the unit, okay? It doesn't mean the number is squared, it just means that the unit is squared, okay? Just that little s there. But all you need to know for the moment being is that the number is 9.81. So we just substitute that in, so here we go. This is the same equation times by 9.81. That means that you can calculate how much weight, which is a force, how much weight any object would have on Earth. if you know its mass. Okay, so when you stand on a scale and you go, oh, I'm trying to put on muscle, it's just not happening. Okay, you just put in that value you see on that scale. So if your mass is 45 kilos, you can calculate your weight force. So I'm going to use a little calculator here to save us all time. And 45 times 9.81, I get a, that's not the right number of digits, 45 times 9.81, that's more like it, 441.45. What's the unit? The unit is newtons, the letter N. It has to be a capital letter. If it's not a capital letter, you've done it wrong, okay? Capitalized letter is for newtons. That's a measurement of force. Okay, so that's basically the force equation. If you can calculate the force for any given mass, then you're in good shape. One thing I will stress to you is that this magical number of 9.81, it's a measurement of how quickly things accelerate to the ground on the Earth. So if you chucked an object out of the window, like a bowling ball or a shot put, it's going to increase its speed by 9.81 every single second. It's going to increase its speed by 9.81 every single second. And so that's an acceleration value. You'll have a different value if you're on the moon. It'll be a lot less. I think it's around 1.6 or something. If you're on Jupiter, I think that value is around 24.5. So much stronger. So if that number is true, okay, so we'll take the same object, okay, and same given mass, so 45 kilos. And let's pretend I'm calculating for the planet Jupiter. I think it's around 24.5. Okay, I'm going to put a squiggly line underneath that because my memory is not too good. But I will get a much, much stronger force of weight. I'm going to get 1,102.5 newtons of force. So that's more than double the force of weight you would have on the Earth. Okay, going to move on.
So, just before you move on, Alice has got to answer. She's got a couple of questions. I've checked the chat for questions.
She's got a lot of questions that will take a lot of time. Let's see.
So, number 5, A, B, and C has been asked by somebody else as well, so maybe at least that one.
Yeah. I was going to do question 5. Go back to yesterday's questions, which is also Brooke's question. So I hope that overlaps for Alice. We go scrolling to question 5. I presume that both of you have asked about part B. Question 5, part B, which is about the flowers. Okay.
So she's got C. Let's see.
Okay.
Got A, B, C.
Okay, question 5 ABC, and this is part B section of the paper. It says Rob has $10.35. Nicole has $8.25. Neil has $9.90, and Danny, still there. It's fluctuating. Danny has $10.80. They want to buy roses for Mum, so Fantastic Flowers sells white roses for this is roses, $2.50 each. Okay, so the first part of that question is determine how many roses they can buy together. So, well, I have to figure out how much money they have together. So that's going to be number of roses is going to be equal to, and I'm deliberately doing keyword structure because looking at the answer scheme here looks like also the start of section B, it says to use keyword structure wherever possible. So I'm going to do that. So this is my K step of keyword. I have to add up all their money together. So let's add that together. 10.35 plus 8.25 plus blah, 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 blah. Everything all divided by how much the roses cost. So that's going to be $2.50. I'm going to punch that through a calculator here. So I'm just going to add their pocket money together. 8.25 plus 9.9 plus 10.8 equals, so I'm going to get $39.30, all divided by $2.50, divided by $2.50. The strategy you could apply here is you could multiply top and bottom by 10, and then you get basically 393 divided by 25. You could put that through short division. So that's one other option of doing it. And I'm going to get a result of 15.72 roses. But that doesn't make sense. You don't get 0.72 of a rose. Am I going to round up or am I going to round down? Well, there's a question. I'm going to round down because it's not... The person who's selling flowers is not going to give you an extra flower just because you have almost enough money. They're only going to give you as many flowers as you actually can afford. So the number of roses can buy is 15. Okay. Moving on to the next letter. B says, determine how much change will be left over. Well, they'll have, what, 72 cents? No. How much? Oh, I see. So change would be equal to how much money they have subtract the cost of 15 flowers, right? So they have $39.30 collectively. Remove how much 15 flowers cost. So let me just do 15 times by the $2.5 each. So I'm going to get 15 times $2.5, 37.5. That's going to give us $2.25. Did I calculate that right? That doesn't look right. I probably did some maths wrong here. I'm just going to go back and do this on the calculator. $39.30 remove $37.50. Yeah, it should be 1.8. Sorry about that, folks. I tried to do it in my head too quickly and I made a mistake. Often when I do that, I will double check myself and go, is that right? No, that's not right. So we'll have $1.80 left as change. Okay, letter C of question 5. Fantastic Flowers has a special offer if you buy a dozen white roses. A dozen equals 12. Okay, that's just, double means 2, triple means 3, for example. Dozen means 12. So if you buy a dozen white roses, you get a 30% discount. Calculate how much they would have if they save with this discount. Yeah, that's a little confusing, because does that mean you save 30% on every 12 roses? Or if you spend 12 or more roses, do you get 30% savings across everything? So I think that's probably the reason why the answer scheme here has the two possible solutions. So I guess I could go with the easier option, which is to calculate 30% savings on everything. So no, I probably should solve it on the harder variation of this problem here. 30% of 12 roses. So that's going to be, they could buy 15 roses. That means that they have 3 roses plus the dozen roses. So we know that the cost is going to be the cost of 3 roses. So let's do 3 times the price of those roses. And that'll be its own little part of my calculation. And then I'm going to do the cost of 12 roses. Yeah. So that's going to be its own little calculation here. I'll change color for this one deliberately here. It's going to be 12. It'll be 12 times the cost of roses. And then I'm going to reduce that result by 30%. How do I present this without confusing everybody? Because what my brain wants to do is just this. Okay, that's what my brain wants to do, but I'm thinking for you guys, you have no idea what I just did now. So let me just try and think of a way of showing you how I got to that. I want to scale this down. Okay, so let me just do a little side proof here. If I have $32 and I want to show that I have 100% of that, I'm just going to times it by 1.0. If I want to show that I have half of that, okay, I can show that as, or 50% of that, I can show that as 0.5. I think you recognize that. Well, basically 50% is 50 out of 100, which ends up being 0.5 if you've done the decimal tricks before. Okay, so that's what I'm thinking. Well, if I want to show that I've removed 30%, so what's 100% remove 30? Well, I got 70% remaining, so 32 times 0.7. That's where this number is coming from. So I want to use this to scale down the total cost of 12 flowers by that much. Scale it down, because I've removed the 30%. So that's where I'm headed to. I hope this makes sense to people. Okay. I'm going to remove this. So 3 times $2.50, I'll get $5,750. 12 times so I should get 300 times 0.7. If I've made a mistake while trying to calculate these things by hand in my head so fast, please everyone just yell in the chat if I've done that wrong. And my wife will let me know I'm wrong. 300 times by 0.7 will just be yeah, I think that's right. Does that make sense? Does that number make sense? They only have $39. I see what I've done wrong. It's not 300, it's going to have a decimal place. It's going to be right there. $3. Come on, come on. I've done this wrong in my head. Give me a second, guys. 12 times. I think that's my answer. 30. Therefore, I'll have. That looks more like it. I can even double check on my calculator here. 12 times $2.50 is 30. So this is right. Times by 0.7. 30 times 0.7. 21. This is right. Okay, okay. We're good now. We're good now. Everyone can stop yelling at me in the chat.
Sorry,
no one was yelling?
except one person that just said yell, which the other pretty much.
Alright, and now I just add these two figures together, so 1 plus 7 is 8. Yeah, I think that's it. Did I answer the question right? That's, again, like you see my strategy here, where I'll work and I'll think I'll get to an answer and I'll just go, did I answer the question? So I'm looking back over it one more time. Fantastic Flowers has a special offer that if you buy a dozen white roses, you get a 30% discount. Calculate how much they would save. Oh, not how much they spend. It's a question about how much you save. So that's going to be a difference. When you save, there's going to be a difference between the full price and the discounted price. Let's do savings is equal to the full price, which they spent.
So just
Mm-hmm.
so in the chat, so like I noticed for this question, it explained at the top it was $39.30, but when it was at the discount, it was $37.50.
Sorry. Repeat that again.
It explained at the top it was $39.30, but when it was at the discount, it was $37.50.
39.50.
$37.50.
$37.50 in part B. So I think they're referring to this number here, which I got from here. So this is how much cash they have. So I'm even drawing making that look like a $sign bill. That's how much money they have, and we know they can buy at most 15 roses. So they have to spend 15 times the cost of each rose. So 15. Just double check that. 15 times the cost of each rose. I should get, this is how much it's going to cost them. So it's going to be the difference between how much money they have, remove how much they spend. So, did I make a mistake already? No, I haven't made a mistake yet. So they would have spent at full cost $37.50 for 15 roses, which is where I've brought this number from. Okay, and remove, let me just use it back, remove the discounted price they would pay if they have the deal. So I'm going to get, calculator again, $37.50, remove $28.50. So they're going to have a savings of $9. And you'll finish it with Kiwa, they will save $9. Whew. Hope that got in before Alice had to leave. So that's question 5C. And that's the harder interpretation of the letter C. The simpler interpretation would basically have 15 roses times 2 is 50, all times by 0.7. That'll be the simpler way of solving it. That takes care of Alice's, sorry. Look, we're at a full hour at this point, and the connection has been a bit sketchy, so I'm just going to do a quick check. Sweetie, are we still okay to keep going a bit longer? Or?
I'm happy to going, yeah.
Okay, right. Well, everyone say thank you to my wife because she is happy to keep going for a bit longer. Let's see how many questions I can get through. So I'm going to go back to yesterday's questions, just because Brooke has one here about, she wants to check one of her ideas here. Brooke asks, can you check if my theory is correct? Skydivers are able to accelerate by turning body because it decreases the amount of surface area, therefore decreasing the amount of basically air resistance. Yes, you're right. So if you have a skydiver like this, okay, that means that all the air particles will be having a lot of contact around the underneath of your body. If you rotate your body, so now you are, I don't know, let's go feet first. Okay, now if you're going head first, you will have a lot less surface. Because if you think about it, all of this, well, that's a bad color. All of this surface here is catching on the air particles. When you go head first, only that area there, which I think you would all agree is a lot less surface area, therefore a lot less air collisions in your face, therefore there's a lot less resistance for you to pass through the sky. So that's why you would accelerate after you change direction. Lachlan asks, this is question 40 from yesterday. Lachlan asked, how to convert a fraction into a percentage? Okay, so 4/3 into a percentage. Okay, the basic process is you multiply your answer by 100/1%. That's basically the process. So it's going to be 400 divided by 3%, and from there you will have to do a short division because we're going to have decimals as our answer here. So let me just go, how many times does 4 fit into 400? So it fits in there once with one remainder, fits in there 3 times with one remainder, fits 3 times. I think we can see that we've got a recurring pattern here. So we're going to get a result of 133.3 recurring percent. You will sometimes see a fraction form where you can easily scale it up. So if I've got 4/5 and I go convert that into percentage, very quickly I can see that I can quickly scale the number 5 into 100 by multiplying it. So 5 times 20, 5 times 2 gives me 10, so 5 times 20 gives me 100. If I do the same scale top and bottom, I will basically convert it into this form. Oh, no, that's wrong. Should be 80 over 100. And we know that anything out of 100 is basically what the definition of percentage, so the answer is 80%. Hope that helps. That's number 40. 41, sorry. What does coefficient mean? Coefficient means basically any number in front of a pronumeral or in front of a letter. Okay, so if I've got if I've got this expression here, I've got a coefficient of 4, okay? I've also got a coefficient over here, but it's invisible. Can you see it? How many copies of the letter B do I have? Well, you can see it's just one letter B, isn't it? So there is actually an invisible number 1 that lives there. We generally don't write the number 1 too often as a multiplier in algebra because 1 times anything doesn't really change it. So it's one of those things we sort of do for short. We don't really write the number 1 very much. So that's a coefficient. And how to divide decimal places by decimal places. I did that yesterday, Lachlan, in the earlier question. I think it was one of Tanya or Lauren's questions from yesterday's stream. So we can tick off question 41. 42 is from Mackenzie. How do we do in the equation in science? I think that was Mackenzie's emailed question. I didn't see which equation she was referring to, so I might have to catch up with her next week. Going back to the chat feed, question 1 says, if we put lowercase n instead of capital N on the test, will we fail that question? Technically, technically the lowercase n is incorrect, mainly because with science there's only so many letters of the alphabet we can use. Like think about it. So I think you're all familiar with like the letter M represents maths, right? Okay, so it means that out of all the alphabet we can't use the letter M for anything else. Okay, so we can't use the letter M for the value of momentum. They both start with the letter M, but M's already taken. So we have to use a different letter of the alphabet. And so it's like, well, we've used up all the letters of the alphabet for English, so let's start picking other letters that we can find. So we use Greek. So the letter we use for momentum is rho. Okay, all right, so that's a Greek letter. Notice how it doesn't have the little stem for the letter P. It's a little different, okay? Rho, and that's the symbol for momentum, right? Same thing happens for the letter lowercase n. N is typically used often in maths for integers of between 0 and infinity. It's usually for something that's counting upwards. So I think you saw in the early example about the mass of the little mouse for n number of weeks. Okay, you can see there's the letter n. Okay, it's almost always used in this way. It's a counter, I suppose, is a simple way of imagining the letter n. So we can't use lowercase n. It means something different. So you have to use capital N. All right, capital N is the way to go. That means newtons. I'm sure lowercase n is also like a bunch of other different values. Cochrane asks, go over that balance. What over a balanced force is, please? I think I've already done that one, so that's number 1 you can tick off. Brooke from chat feed says, can you please briefly explain how inclined planes work? Inclined planes are ramps. Okay, this is inclined. I think this might be something related to the word recliner. So you've got like a okay, so this will be a recliner. Or that person has reclines, which I think re might mean backwards, and incline might mean upwards. I don't know, but it's effectively a surface that has been tilted away from the horizontal. Okay, and the reason why these things make life easier is that if you have an object that's really heavy, I don't know, let's say you've purchased, an anvil, and anvils weigh, depending what size you've bought, but a traditional blacksmith's anvil is like 500 kilos or more. It's incredibly heavy, and it's incredibly small, which makes it incredibly dense, which makes it very difficult to move. So you might stick some wheels on it, for example. So here's some like skateboard wheels. And then you might be able to push it up, okay? You might be able to lift it up into the first floor of your house, okay? Using a ramp. This will be a lot less effort. Let me use orange now. This is a lot less effort than trying to lift the anvil straight away. So here's my anvil again. And here's my poor little body. Okay. The reason why this is so difficult is because the weight of that object is basically you have to apply more upwards force than the weight is pulling the object down. You are in exact opposition to the direction of the weight force by trying to lift it vertically to the first landing of your house. However, when you have the anvil sitting on the ramp, I think you can see that most of the weight of that object is resting on the ramp itself. That means that you only have to overcome just a little portion of that weight to actually roll it up and into your house. So you can still achieve the same elevation, so you can get it from the ground floor to the first floor of your house. You can still get it there. It just takes more distance to get you there because you have to travel all the way up this ramp surface rather than just going up this direction. But it does mean that you're not trying to overcome the entire weight of the object because the ramp itself is doing most of the heavy lifting for you. So I think you'll find that if you have a really steep ramp, okay, so here's my ramp here, and there's that anvil again, I think you'll agree that most of that weight force is on you, right? But if you have a very, very, very gentle ramp, then pretty much all that weight is sitting on that ramp and very little of it is on you. So this will be so much easier. This will be so much pain because the ramp is not really doing much to help you. I hope that helps. Is acceleration usually gravity? No. Acceleration is from any force. So if I do, I'm just now being silly at this point, sillier than usual because it's really late and I'm just going over time here. So let's pretend that I might have muscles, okay? Okay. And let's pretend I've got some like cool sunglasses on. Alright, so there I've given you a punch to the face. Okay. I have caused your skull to accelerate. Okay, doesn't mean gravity's done anything, it's just me hitting you. Alright, so that could be a tennis ball hitting you, it could be a basketball hitting you, it could be teacher hit, it could be anything. So another one is you could have like a rocket. The rocket is causing the object to accelerate by forcing gas out backwards, which then forces the rocket forwards. And that's nothing to do with gravity at all. So acceleration is not always gravity. Gravity only influences objects by their weight, by their mass. Okay. I've already done whatever balance force is, sweetie. So number one. Okay. And I've already done. Is an inclined plane a force? Yeah, inclined plane is a force multiplier. So going back to finishing off Brooke's expanded question here, an inclined plane is a force multiplier if the inclined plane is nice and gentle, like this. Not so much there. I mean, it still is technically making the job tiny bit easier because the ramp is supporting some of that weight. But I think you'll agree that this type of this sort of gradual incline is going to be much more force multiplication. Question 9A of the test.
Is it usually number 3 and 4?
Oh, 3 and 4. So what are constant terms? Constant terms are, let me just go back up to here. A constant term, so these ones here were coefficients, right? A constant term is a loner. Okay? They don't have any letters of their own. They are really, really sad. Okay? Because they don't have any pronumerals next to it at all. Okay? So that's a constant term. Can you explain how to take off a discount? Okay. Discount. You have two methods. Okay. So let's say I've got $200 and let's say 25% discount. Okay. So I have two options to solve this one. So I'm going to do the first one in red. First option is that you can take 25 discount of 200. So I'm taking away cost from the 200. So it's going to be the 200 cost. Remove the 25%. 25% of what? 25% of is multiply by the original item, right? So that's one option. All right. So I'll get 200 subtract 25 over 100 times by 200 over 1. This is just me just rejigging some maths here. I can now cancel out some zeros that way. And now I get a result of 200 subtracts 25 times 2, which would give me 50. 50 over 1. So it's basically 200 remove 50. That gives me 150. That's one option. The other option that you could do, this is option 2, is you can take 200 multiplied by the remaining percent. Okay? So if I've removed 25%, then how much percent is remaining? Well, I've got 75% remaining. So I could do it that way. 200 times by 75 over 100. Okay? And then I can just convert this one here into a fraction as well. And once again, just crossing out some zeros. Cross simplification. So it essentially becomes double 75 over 1. So that's the same thing, 150. So that's two options on how to solve a discount. Brooke, do we know how Do we need to know the formulas for the test? Yes, you need to remember the formulas. Your formulas are mechanical advantage is load over effort, and force is mass times acceleration, or if you're talking about weight, you can have force weight equals mg. I think we were doing gears the other day, but I need to revisit that on Monday. What is potential energy? Potential energy is the energy. Potential energy is stored energy. Okay, so my mobile phone has energy in it. I think you would agree. It's a device. It has battery power. Okay, when I plug it in, I can charge up the device with energy. Okay, and that type of I've stored it as potential energy in the battery. That means when I unplug it and then I start to use the device, I can now harness or use up or spend the potential energy that I have put in it. You can do other kinds of potential energy. So some things. Sorry. I need to go grab something. Okay, I'm back. Okay, other things can store energy too. So I can store energy in this napkin. It's almost like... No, it's not magic, it's just physics, okay? So there's another form of energy. So this type of energy we call chemical energy. Okay, I'm using electricity to turn the chemical reactions in the battery so it's ready to go. I can store it in there, potential energy. I can also create potential energy in any object raised above the ground, because when I let it go, okay, I can turn that into energy again. I can turn that into movement. So when things move, we call that kinetic energy. So just by lifting it up, I can create, I can basically spend that energy. If I have a heavier object, I can get a lot more movement out of it, so you have a lot more energy stored in it. We call it gravitational potential energy, but that's beyond what we need to know for year 7. Question 9a. This should hopefully be our last one. Question 9a. Question 9a. Do you know who asked the question 9a? Because I'm looking at the exam paper for maths, and there's no part A, B, C. It just says. Okay. Well, I will just solve the one from question 9, part.
9A. Question 9. Something called. Okay, I don't remember what this is.
9a of science or 9a of maths? Okay, so there is no question 9a of part B. There is just question 9. Is this the one he's referring to? So if you can confirm what you're seeing over here, is it Brandon? Is this the one you're looking for? Or are you asking about question 9a from the first half of the paper, which would be simplifying? Because you also got question 9.
So it's part A.
Okay, part A. Alright. Let's do that one, which is to simplify 9a subtracts 2a squared plus 6a squared. So yeah, I did this one yesterday on the live stream, but essentially the idea is that simplifying means to make the answer concise, or to basically gather all the things together, calculate what you can and leave behind what you can't. Basically make the thing look nicer, make the thing look smaller as a result. So here I can see I have some pronumerals, right? And I'm just jumping the gun here. A squared is not the same thing as A. You can only gather terms together if their pronumerals, their letter combinations, are exactly the same. And I was showing yesterday that the reason why this does not belong with these is that the letter combinations are different. So if I expand what a square is, that's the same thing as A times A. And now if you look at it, these are not the same thing as that. Okay? These belong together because they're the same combination, but 9a is the only one by himself, so he's all sad. He has to stay by himself. He can't be gathered. He can't be solved with anybody else. And now I just have to solve. I now have to solve what -2 copies plus 6 positive copies. So it's basically -2 plus 6. So I should get a result of positive 4AA, which is the same thing as 4a squared. I will make a note that one of the parents picked up that I made an error when I was trying to recall this question off the top of my head on yesterday's live stream. Let me just scroll back, see if I can find it. Getting dizzy just looking at it all. Yeah, when we were doing this, I made a mistake. This answer should be positive. Right there. That should be a positive answer, because -2 plus 8 is going to give you a positive 6. Okay, this is when I was trying to recall this specific question that Brandon asked. I hope that helps, Brandon. And I think that takes care of... Oh, there's more questions. Not too much. Okay. What does torque mean? Torque means a twist force. Is it on the test? No. Torque is not on the test. It's just a name of a twist force. Number 2 says, are wedges simple machines? Are they able to support with less effort than people's hands? I think a wedge is a simple machine, and it does require less effort. So I think there was a guy... Let me just see if I can draw this. Okay, we got Captain America. Okay, and there was a scene where he literally rips apart a block of wood. Okay, I think we can all agree that none of us can do that. That takes a tremendous amount of force. It takes a tremendous amount of effort. Okay, so for us mere mortals, the way we can achieve the same result is to use a wedge. Okay, so okay, so just give it some color, and then give this one some color. And then maybe stick something on it like a handle. Okay, so here you can achieve the same result by literally slamming into the block of wood with a axe or splitting axe. You have a small amount of downwards effort. Okay, obviously when you swing, you can also swing in the same direction as gravity, so that also helps you. But that is a lot less effort than Captain America does this way. So for that small amount of effort, you get a tremendous sideways force from that wedge. So I would from that thing where it takes a small amount of your effort to do a tremendous amount of work, or a tremendous amount of sideways force. From that, I would agree. I would make a case that the wedge is a simple machine that is a force multiplier. Okay. What is a cross section? A cross section is it relevant? I don't know how to answer your question if it's relevant with any certainty, but I just want you to imagine here I've got a tree. Oops, the highlighting here is not doing too great. Okay, so here I've got a tree, and then here I've got a cat who's trying to cut the tree down. And let's say it's going to be construction cat. He's got his tail, he's got his little helmet on, and he's got his safety glasses on. A bit dark. And let's say his chainsaw is red. Alright, he's got a red chainsaw. Okay, a cross section is if I cut here and then I take my eyeball, okay, and I look at the area that I just cut down. So here's my nose. Okay, hope that looks obvious. That's his nose. If I look down at the tree, what would I see once I've cut the tree down? I would see essentially this from above, wouldn't I? Oops, that doesn't look right. Okay, I'll be viewing this. Okay, this is the cross section. Okay, so you could do cross sections of lots of different things. You could be the cross section of, I think there's like a really tall like building or something in Dubai, and if you looked at its cross sectional area, I think you'll find that if you sort of chopped it down and looked at it from above, you would see that the Dubai Khalifa, Kuala Lumpur, I don't know what it's called. Okay, you would see something that resembled a little bit like that. Obviously elevators inside and rooms, of course, but that would be the cross-section view of it. You don't need to know that for your test, as far as I'm aware, but it is a way of describing what you're looking at. Is centrifugal and centripetal force on the test, and what do they mean? No, they're not on the test. Well, people get people get really hung up about centripetal and centrifugal force. So basically, the idea is that if I have let's see. Okay. If I was to swing the bucket around, okay, but it's fixed in his hand, then there is going to be a bit of tension on this rope, okay? So obviously the cat is pulling the bucket towards him, and the bucket itself is pulling. It's trying to fly away, and this phenomenon is sometimes described as centrifugal force or centripetal force, and there's a lot of debate as to what's the correct term. So I'm not going to get too much into it, but basically the idea is that when you want to swing a bucket, the bucket wants to, according to Newton's first law of motion, is that the bucket wants to move in a straight line in its original direction of motion. So if I've got to this stage here, the bucket wants to keep moving this way. Okay, but if I grab this and move the bucket, let me just see if I can just grab the bucket itself. Okay, so it wants to keep moving that way, but when I get to this part of the journey, it can't go in a straight line because it's attached by a piece of rope. So it gets pulled down. Okay? So, and it's going to resist that because it really wants to go this way, but the rope's pulling it this way. So it's almost like it's pulling away from the rope the entire journey as it goes around the cat. Okay? So this effect of the bucket wanting to pull away, that's part of the story of centrifugal or centripetal force. And I think that is it. That's all their questions?
Yeah.
Alright, we will end the live stream. Thank you very much for coming. I will see you on Monday, Tuesday, etc. Unless you are overseas, and I will not see you. Alright, bye-bye.